Okay, here we are again. I'm showing you here the summary of statements which are equivalent, and actually they have special names. One of the famous laws of equivalence is the one that we often observe, no, in many examples that we have. We call that the De Morgan's laws, okay, which says that the negation symbol can be distributed over P and Q, and the effect of that negation to P and Q is the P will be negated and the and will be changed to or, and Q also will be negated. Okay. Correspondingly, the effect of the negation to P or Q is that P will be negated, the or will become and Q will be negated. So that's what we call the De Morgan's laws. We can prove that actually by using the truth table. Other important laws of equivalence are the commutative laws, which says that the two propositions commute or can be interchanged over the and. Okay, so P and Q is equivalent to Q and P. Also, P or Q is equivalent to Q or P. Then we have the associative. Okay, so as long as they have the same connective, logical connective, you can rearrange the, you can regroup, okay, without changing the meaning. Same is true with this one, right? The distributive loss is another important law. The P can be distributed over Q or R under the and. So if you have P and Q or R, can be distributed as P and Q. So you have P and Q, then or P and R. This may be familiar to you when we distribute numbers, no, over yung distributive property of multiplication over addition, if you remember that. P or Q and R, when you distribute P to Q and R, that would be P or Q and P or R. Other laws are the identity laws. Now, the T here is our notation for tautology, meaning this is a proposition which is always true. Okay, so when you connect that with P using the connective and, P and a tautology is always P. On the other hand, P or C is a contradiction. So P or a contradiction is equivalent to P. Negation law says that P or not P is a tautology. Okay, we have checked that from our previous exercises. Then P and not P is a contradiction because under and this is always false. Okay, because when one is true, the other one is false. So using the connective and, when one is false, that's always false. So that's why you have a contradiction. The double negative law says that the negation of P is always P. Idempotent law says that P and P is P, while P or P is also P. Universal bound law says that P or T is equivalent to T, while P and a contradiction is equivalent to a contradiction. And then the De Morgan's, then the absorption law. Look at the form for the absorption. That's quite an interesting law, because you have P or P and Q. That's always P. Now this one may vary as long as P and P here are the same. Then that's always equal to P. Also here, right? That's always equal to P. Now, let's illustrate the usage of the laws of equivalence. I mean, there is an alternative method. This is an alternative method of proving that two statements are equivalent by using the known laws of equivalence without using the truth table. You can also use this to show that a statement is a tautology or a contradiction without using a truth table. I have here some examples that we will use, okay, to illustrate the idea. Let's start first with letter A. Okay. It says we're going to prove that the two statements are equivalent. Normally we construct the truth table for that, no? But suppose we will use the laws of equivalence instead of the truth table. So let's try. For example, number 4, letter A. Let's start first with the more complicated statement, and then we will simplify this until such time that we obtain P, okay, at the end. So we have negation of the negation of P and Q and P or Q. Okay. You notice here that there is the negation symbol outside. So the tendency is, the natural tendency here is to distribute that, no, inside. And what are we applying? Which law is to be applied when we distribute that? We will apply the De Morgan's laws. Okay, the De Morgan's laws. So that's our first step now. So we distribute that. We have negation of the negation of P. So let's see. We have negation, the negation of P. Okay. Then remember the effect of negation to end. It will become or. Then negation of Q. Okay. Then let's just copy P or Q. Okay. So what is our justification for this step? This is actually the De Morgan's law. Okay. Now for our next step, notice this, we have to simplify this part. Okay. Which law allows us to simplify this? We have what we call the double negative law, if you remember that, no? Property number 6, or law of equivalent number 6. The double negative cancel each other, so we're left here with P na lang. Then you have or negation of Q, then and P or Q. So this is double negative law. And next, okay, if you notice, this is actually the result of distributing P over negation of Q or and Q, no? In other words, this is the result of distributing something. And what is that something? It's actually P. When P is distributed over negation of Q and Q, okay? If you distribute this, you have P or negation of Q, which is that statement, and P or Q, which is that statement. So basically, this is the reverse of the distributive. Okay, so in a sense, we apply here the distributive law. Okay, then what should be done next? We write P, then or, but with this negation of Q and Q. Okay, we refer again to the laws of equivalence. Negation of Q and Q, that would be this one, right? Negation law, which is P, and negation of P is a contradiction. Okay, so this is a, sorry, let's erase this one. This is a contradiction. This is a contradiction. And then, what is P or a contradiction? We again refer to, by the way, the justification for this one is, what's that? That's a contradiction. So this is negation loss. Okay, you can always refer to this one, no? To this table, the laws of equivalence. Now, what about for this P or C? Is P or C here is P, so that's identity loss. So this is P, and the reason for that is identity loss. So that's it. We're able to prove that the two statements are equivalent by using the laws of equivalence. And I actually find this easier to use than using the truth table, because the truth table requires a lot of time. Although this method requires using a lot of thinking also, but if you get used to it, then you'll find that it's easier to use. So I think we'll end here, and thank you.